Hello, welcome to my presentation on honeyPLC, a next generation honeypot for industrial control systems. My name is Michael Doran. So I'll be discussing a brief introduction along with background and related work that the authors provided in their paper. We'll discuss limitations of current honeypots as well as the architecture of honeyPLC, and we'll wrap it up with some evaluation results, discussion, along with future work, and finally a conclusion. So, industrial control systems provide management and control capabilities for mission critical utilities. Some examples of that would be nuclear, power, water, and transportation. Within these industrial control systems, we have programmable logic controllers. These PLCs play a key role as they're the bridge between the cyber and the physical world. So PLCs, as well as industrial control systems, are becoming increasingly interconnected, which means that they're ultimately more vulnerable to cyber attacks. So since the infamous Stuxnet attack in 2010, we've seen a steady increase in cyber attacks against industrial control systems. One example of this would be the 2015 Ukrainian power grid cyber attack that affected almost 250,000 people. Fast forward to 2025, and of course you can see that the number of ICS related attacks has increased by orders of magnitude. In these scenarios that are presented here, PLCs were the primary target of the Stuxnet malware attack, as well as the Ukrainian power grid attack. So who's attacking these industrial control systems? They're what are known as advanced persistent threats, and they have a portfolio of attacks. Unfortunately, as a cyber defender or someone who's trying to mitigate or defend against their industrial control system against malware such as Stuxnet, they have to rely on public knowledge or intelligence disclosures, which don't always cover all of the PLC attacks that exist, right? So one example of thinking about this is if you have a playbook, you don't want to show your enemy all of your plays because that is how you'll have that element of surprise or be able to operate covertly. Another reason for this is that manufacturer disclosure often takes time, and so you're not always working with the latest information that is available. So current honeypot implementations for industrial control systems ultimately fail to provide sophisticated attack techniques. What ultimately happens is they are low interaction, they lack complex functionality, and they restrict any sort of valuable data that could be gathered from an attack. So what exactly is a honeypot? This is a decoy system or network designed to attract attackers, observe and log attacks, and use that information to learn from real-world threats. You can classify honeypots on two sides of the spectrum. You have low interaction, which simulates a limited set of services and interaction, and high interaction, which goes as far as emulating full systems with real services or applications. So a bit more on PLCs. The authors define PLCs as industrial computers used to automate machinery and processes. They perform logic functions based on input signals. So some examples would be sensors, switches. Those PLCs, they'll control output devices such as motors, valves, or lights, and they're designed for real-time operation. And so some key features that you would find in a PLC is that they're rugged and reliable, so they're meant to be deployed in harsh environments. They're programmable, modular, and they have deterministic timing. In a typical workflow you might see a PLC employed in is it will read inputs from, say, sensors or switches, execute logic to make decisions based on the input from those sensors or switches. It will update outputs accordingly, and it will repeat that cycle continuously. So now that we've sort of baselined what is the threat, why the threat exists, as well as what PLCs are and how they're employed in industrial control systems, we can switch gears to identify how an attacker might observe or discover a PLC that exists today. And so there are some pretty popular network reconnaissance tools. Starting at the top, we have Nmap. This is a pretty popular and sophisticated open source tool for operating system and service detection. The way it works is it'll send raw IP packets and analyze those responses. And the report it ultimately gives with respect to operating system guesses comes along with a confidence score. So for example, you can imagine a Windows operating system or a Linux Ubuntu operating system would have a pretty high confidence considering there are a lot of those systems deployed. And so attackers can use this information to fingerprint devices, in our case, PLCs. So PLC scan is another tool that the authors identified. This is a specialized scanner for industrial protocols. It's very useful in detecting devices that speak the S7 COM protocol as well as Modbus, and it'll go as far as revealing the PLC model, firmware, and hardware ID. So beyond the two scanners, we have Shodan along with the Honey score that is provided by Shodan. So this is a search engine for internet-connected devices, for example, PLCs. It will find any public-facing PLCs that exist today and index them. It can also go as far as providing a Honey score, which will estimate if a device is a honeypot or not. So the way it works is if it scores a 0, it's more than likely a real device, and if it scores a 1, it is a honeypot. So the objective here that the authors want is to score as low as possible, if not a 0, for their honeyPLC implementation. And ultimately, the way that Shodan will work is it'll also look for specific identifiers. So say, for example, a PLC is deployed within an AWS environment. That would be something that is suspicious. So in this scenario, you would likely see a score closer to that 1, indicating honeypot. So the authors did a pretty extensive evaluation on related work. We won't go over each one of these pieces of work in detail, but we'll stick with an example here. So orienting to the top of this table, you see the keys, starting with the red X, which will indicate no cover. We can look at any of the features that are outlined within the columns. So for example, gas pot in the first row and extensibility in that second column would have no coverage. And so what the authors were able to do is evaluate based off of these 7 features and identify scenarios where there's no coverage, or in the case of gas pot, limited coverage. So that feature of out-of-the-box PLCs, so the 4th column in the first row, this would likely indicate a feature where Gaspot was able to sort of provide some default configuration, but ultimately lacked coverage with respect to what the full PLC profile should look like. And finally, ending with what optimal coverage is, so sticking with the same example, logging was a functionality of Gaspot that provided optimal coverage. So this means it had the ability to log any sort of interaction or engagement someone had with this honeypot for the duration that they were working with it. So you can imagine, it looks to me that the only thing that really implemented all of these features with optimal coverage was honeyPLC, which is down there at the bottom, indicating, more or less that high interaction honeypot, which is what the authors were going for. So now that we have an idea, again, of what these threats are, where the current state of the art is, it's really good to sort of juxtapose, some of these limitations against the sophisticated malware that exists. So we already discussed about Stuxnet. This was sort of the first ever documented cyber warfare weapon. The first case of geopolitical influence from a cyber perspective. It specifically targeted Siemens PLCs, and it was spread via USB sticks. So it circumvented any air gap measure that was in place to bolster that cyber posture. Moving on, there was the author cited the Kamuri incident, which compromised water supply along with hundreds of ICS devices and disrupted operations. And then finally, Crash Override, which was malware designed to disrupt ICS networks using electrical substations. And it's so sophisticated with respect to protocols, it indicates that the attackers of this group that developed it had access to specialized industrial equipment and subject matter expertise. And so again, going back to the limitations that exist for current honeypots and the sophistication that we're up against today, it really means that the level of high interaction that honeyPLC is attempting to achieve here actually really is attempting to solve a real world problem of learning from very sophisticated attacks, so that way we can prevent them. And so how does honeyPLC overcome some of these limitations? So going back to that table, or thinking back to that table, extensibility is really this idea of extending the functionality to different brands and models of PLCs. And so honeyPLC equips or developed this honeyPLC profiler tool that can be used to baseline different brands and models. And so what that baseline ultimately does is it gives you an idea of the network protocols that honeyPLC needs to support by means of these dedicated PLC profiles. And all of that is in support of this limited covert operation feature, which provides advanced network simulations. So you can imagine if a PLC communicates over HTTP, SNMP, Modbus, etc., you would want this profile along with this architecture to sort of deploy and emulate those same features. And ultimately, if someone actually is deceived by your honeypot, you want the ability to collect the malware that they inject into it. And so the authors developed a novel feature to collect ladder logic that a would-be attacker might upload to this system. So switching gears a bit, let's actually take a look at the honeyPLC architecture. So this architecture is comprised of 7 components. Let's see here, 6 out of the 7 are actually the software stack. So orienting to the left, we start with number 1, the PLC profile repository. This profile repository is what makes up the baseline profiles that were generated from your profiling tool. So in the out-of-the-box configuration or source code that you can get off of GitHub, there are 3 different Siemens PLCs that are available for you. And these profiles are what are fed into the integration framework starting at the top, along with the network services. But going to the top, focusing more on the integration framework, we have 2 components, the subsystem virtualization along with the personality engine. And then moving down, we have the network services, which are made up of those 3 components that you see there. So a custom S7 application, along with an SNMP agent and an HTTP server. And then finally moving down, we have that interface to the interaction data, which stores any sort of captured ladder logic along with any logs. And last but not least is the attacker, which provides that red stimulus to this architecture. So let's dive deeper into what each of these components are. So in the architecture, starting with your initial setup, you're going to choose a PLC profile from this dedicated repository. So an example would be a Siemens model S7 1200. That S7 1200 profile was an output again from this PLC profiler tool, which automates the creation of a new honeyPLC profile. And the way that this works is that tool interfaces with services such as Nmap, SNMP walk, and wget, and it only takes a single input, which is an IP address. So you can imagine a scenario where you have a host machine that has this honey profiler tool on it. You have a network connected and accessible PLC. You can use this profiler tool with the current IP address of your PLC, and Nmap, SNMP walk, and wget will provide you with the fingerprint, any PLC data that is relevant, along with, say for example, the HTML files for the management portal of that PLC, and those will all be created for you and ready to be pulled into the integration framework. So moving on, what does that process actually look like, and how does honeyPLC support that? So the subsystem virtualization is provided by another honeypot tool known as honeyD. So this honeyD service is pretty popular for performing honeypot operations for advanced network protocol emulation, as well as configuring and setting up or virtualized networks. So this subsystem virtualization will take the results of your profile and leverage contributions from the authors, so specific scripts to allow your profile to deceive services such as Nmap or PLC scan. There is also a personality engine that is sort of orchestrating things in the background here. So in the figure towards the right, you can imagine if you have, say, a remote host conducting an Nmap scan, what will ultimately happen is the personality engine will have that information available via the profile, and any sort of Nmap scan that comes through, that personality engine will be able to collect that fingerprint and use it as a response to a remote host that is actually performing any sort of reconnaissance on your PLC or honeyPLC device. So moving on to the network services. So we have the S7 com server, which is a custom application that the authors wrote in C++. The source was provided by Snap 7 and Wireshark. And what this does is it provides not only the ladder logic capture functionality, but it exposes memory blocks via TCP port 102. So this modified S7 COM server will provide reply capability for any requested information. And there is a logging service that will log any sort of interactions, so information coming from the outside, such as IP addresses, memory block requests, anything that would be useful to learning from an active attack. So one of the other components of the network services was this SNMP server. And so that really provides that SNMP protocol capability. It listens over UDP port 161, and it is actually implemented using a Python application known as SNMP Sim. And then finally, there is an HTTP server functionality or server that's hosted in this architecture as well. This is powered by a service known as Light TPD. And ultimately, the functionality of this or use case of this would be to serve, say, any PLC websites that were extracted from the profiling tool. So this figure on the right was provided by the authors. You can imagine, if someone is interfacing remotely using SNMP Walk, there is a use case right there of how the SNMP agent can grab any of the MIB data from the stashed profile repository and use that as a response to SNMP Walk. Same with an HTTP client. If someone was attempting to access, say, a web management portal that's hosted on the PLC itself, that website would be hosted via Light TPD, and anyone using or requesting would get a response that would be valid and indicate the management profile of that PLC. So then finally, the interaction data layer. So this S7 COM server implements that ladder logic capture feature. So this will ultimately write any ladder logic that's uploaded to the device and stash it into the honeyPLC file system, along with any relevant record keeping that you would want to keep. So any logs produced by the S7 COM server, the SNMP agent, or the HTTP server. Let's see here. Okay, so moving on to evaluation. What we have are the authors described collecting 4 different PLC models. So 3 from Siemens, 1 from Allen Bradley, and 1 from ABB. And ultimately what they wanted to evaluate was 3 experimental questions. Can the honeyPLC architecture support different real PLCs? Can it conceal its honeypot nature from attackers? And can honeyPLC effectively capture ladder logic code? And so the authors went ahead and designed several experiments. The first one being profiling PLCs. So this was really in an effort to answer that first question. And ultimately what we have here is based off of their description in the paper, I created a simple block diagram to represent how they set up their experiment. So starting at the bottom of the block diagram, we have a special power supply that was able to power the PLCs. These PLCs were network connected to a laptop device, which was equipped with the honeyPLC software stack, along with Step 7 manager in Python 3. And so the results of this is that in approximately 5 minutes, any new PLC that was introduced to this setup was able to be profiled with a few challenges. So adjustments had to be made to any of the HTML files that were extracted, specifically any of the images, any of the paths, as well as manual modification to correct broken links. So what this ultimately allowed them to do was expand their capability and extend to different PLC profiles to grab a Nmap fingerprint, which would result in a higher confidence when actually performing network reconnaissance. So the next experiment was, so now that they have these profiles, how resilient is this architecture to reconnaissance? So again, just using the description that the authors provided, I created a very basic block diagram. So their setup consisted of 2 physical hosts, a desktop, which is represented on the left of the block diagram, and a laptop, which is represented on the right. And each one of those systems has that exact software stack, noting versions of each one of those software tools. So what they were able to do is in the same setup, they could also perform additional comparisons. So they implemented GasPot, S7 Comtrace, SCADA, HoneyNet, as well as ConPot. And the idea here is that they wanted to use Nmap in order to determine, what are the results, or what confidence does Nmap return with respect to deploying honeyPLC under these different profiles, and how does that evaluate against any of the other honeypots that exist today. So the results of that, with respect to honeyPLC, it nearly matched the Nmap confidence scores of real PLCs. So we have this diagram over here that maps Nmap confidence. So starting from the top, we have an S7-1200 honeyPLC that was deployed. We can see that in comparison with the S7-1200 real device, that Nmap confidence was anywhere between 96, a little bit above 96% to about 98%, which is well within range of the real one. And so again, each one of these results indicates a pretty high confidence that when deployed within honeyPLC, it measures up to the real one. I do think that the S7-1500 here obviously performed pretty well, but with respect to numbers, 94% confidence versus 98% confidence is not too shabby. So ultimately, it really outperformed any of the other honeypots with respect to realism and protocol interaction. And provided for you are just some notable results of this experiment. So one honeypot was identified incorrectly, and 2 honeypots were identified as Linux, which is, again, sort of something that we noted previously when looking at the limitations of the current honeypots. So the next experiment is that they took this honeyPLC architecture, and they were actually able to deploy it to AWS in their Elastic Container instance. And so this is the setup again over on the right based off of their description. There are 3 instances of the honeyPLC stack deployed, so each one representing the Siemens PLCs. They were able to open up ports 80, 102, as well as 161, and they provided an AWS EC2 instance for the additional honeypots that they were evaluating against. And the Shodan scores were obtained for each honeyPLC profile, along with the alternative honeypots and real internet-facing PLCs, right? So there is something to compare against. Let's see here. And they also pulled in PLCs that were flagged as honeypots. And ultimately, this experiment took approximately 1 week once they deployed each one of these EC2 instances in order to get indexed within 2 Shodan. And so based off of the results of that experiment, what they were able to find is that the honeyPLC's S7-300 profile was actually assigned a honey score of 0.0, so indicating that it was a real PLC that was out there in the wild, which is pretty incredible stuff. The other models were assigned a honey score of 0.3, which matches the actual score for the real S7-1200 PLCs on Shodan. So even though this is a physical device, you have to take into other considerations, and a confidence score of 0.3 is not exactly 1. So I guess that's pretty good results, even if you have a real PLC. So some notable results of the other honeypots is that ConPot was assigned a 0.3 honey score. GasPot, SCADA, HoneyNet, and S7 Comtrace actually crashed when probed. Therefore, they didn't get any sort of score. And so what these results indicate, or reinforce really, is honeyPLC's ability to implement stealth and realism. So that question 2 from the experimental questions that the authors are trying to answer. So moving along, the next experiment is they actually wanted to set up a step 7 manager interaction test bed. And so the way that they were able to do this is they leveraged virtualization. So they deployed guest virtual machines. One of them specifically was a Windows XP environment, which I'm assuming actually had the Step 7 manager deployed to it, although that wasn't really indicated in the paper. And what they were able to do from there is they deployed 3 additional guest virtual machines that contained that entire honeyPLC stack, along with the alternative honeypots that existed. So that sort of is represented again in the block diagram. And the idea here is they wanted to test basically 4 basic workflows, which would be the initial connection using the Step 7 manager. So can these devices go online, and can we interact with them from Windows XP much like I would in an actual industrial control system. Can we perform a function such as memory block listing? So can we retrieve any of the listed, or can we retrieve all the listed memory blocks stored on the honeypot? Can upload test be achieved, and can a downloaded test be achieved, right? So this is really uploading to a memory block and downloading from a memory block. And so the results of that was that honeyPLC supported all of the tested Step 7 manager functions that we just covered. The other honeypots could establish initial connection, but ultimately failed during initial interaction. So with respect to honeyPLC compared to the S7 ComTrace functionality, is that honeyPLC offered more S7 communication functions than the S7 COM server did out of the box, right? And so there were features such as error response handling that was implemented, insert and delete block, a blink LED function for, I'm assuming, Siemens PLCs or maybe a variety of PLCs. It wasn't quite clear, as well as a cancel password function. So moving on, the next experiment leveraged the same setup that we covered, so the AWS deployment. But this was really to sort of capture anyone that could actually interface with this honeypot, so honeyPLC, right? So the goal here was to see if anyone could actually probe this. Anyone that has an internet connection looking for PLCs could probe honeyPLC, and could the authors log any sort of attack that was actually going on at this time. So again, using that same setup, the authors let this experiment run for 5 months, and all received interactions were logged. And so what that amalgamated to was over 5 gigabytes of interaction data logged. It logged a variety of S7 communication commands, which were received across all PLC profiles. More notably, 4 PLC stop commands were logged, which indicates maybe someone was attempting to disrupt operations or just see what they could get away with. With respect to HTTP and SNMP, thousands of HTTP sessions, including authentications attempts, were logged, and thousands of SNMP requests, including downloads of the honeypots MIB, were logged. As far as geolocation interactions go, most S7 communication connections originated from countries that the authors claimed were historically involved in ICS attack campaigns. And so over to the right, I not only provided the stats of those, of those HTTP conversations along with the S7 communication conversations, but also the notable interactions from the geolocation. So indicated in red there were sort of the top figures, so the top contenders, which again the authors claim were pretty involved in ICS attack campaigns. And throughout the 5 months, the authors did not record any injection attempts observed during this experiment. So no malware captured, unfortunately. Okay. So the ladder logic capture experiment in this scenario, it involved deploying honeyPLC, which in this scenario, the authors were able to evaluate that when using a service such as PLC Inject, they were actually able to download any uploaded malware to the system, right? So they were actually able to strongly validate their question 3. The other honeypots were unable to successfully do this. So moving on to discussion and future work. So ultimately, honeyPLC outperforms any of the other honeypots that exist today, especially with respect to stealth. So being able to fool Nmap and Shodan was a pretty big step. It implemented advanced protocol simulation, as well as this profiler tool to implement extensibility, and it provided this ladder logic capture. So some of the limitations that it provides was really no physical modeling, so really providing any sort of input-output based off of ladder logic that currently exists, and of course no Stuxnet level evaluation. The authors would also like to add support for Modbus as well as full ICS simulation, and perhaps add in a malware analysis suite to it. So the conclusions, honeyPLC demonstrated superior performance. It achieved some realistic behavior, offered an immense extensibility tool, and is a very capable defensive tool. Here are some of the supporting organizations for this work, and that concludes my presentation. Thank you.